Astronomy in China has a very long history, with historians indicating that the Chinese were the most persistent and accurate observers of celestial phenomena anywhere in the world before the Arabs. Star names later categorized in the 28 mansions have been found on oracle bones unearthed at Anyang, dating back to the Middle Shang Dynasty, and the mansion system's nucleus seems to have taken shape by the time of the ruler Wu Ding. Detailed records of astronomical observations began during the Warring States period and flourished from the Han period onward. Chinese astronomy was equatorial, centered as it was on close observation of circumpolar stars, and was based on different principles from those prevailing in traditional Western astronomy, where heliacal risings and settings of zodiac constellations formed the basic ecliptic framework. Some elements of Indian astronomy reached China with the expansion of Buddhism after the Eastern Han Dynasty, but the most detailed incorporation of Indian astronomical thought occurred during the Tang Dynasty, when numerous Indian astronomers took up residence in the Chinese capital, and Chinese scholars, such as the great Tantric Buddhist monk and mathematician Yi Xing, mastered its system. Islamic astronomers collaborated closely with the Chinese colleagues during the Yuan dynasty, and, after a period of relative decline during the Ming dynasty, astronomy was revitalized under the stimulus of Western cosmology and technology after the Jesuits established the missions. The telescope was introduced in the 17th century. In 1669, the Peking Observatory was completely redesigned and refitted under the direction of Ferdinand Verbiest. Today, China continues to be active in astronomy, with many observatories and its own space program. Early history. Purpose of astronomical observations in the past. One of the main functions was for the purpose of timekeeping. The Chinese used a lunisolar calendar, but, because the cycles of the sun and the moon are different, intercalation had to be done. The Chinese calendar was considered to be a symbol of a dynasty. As dynasties would rise and fall, astronomers and astrologers of each period would often prepare a new calendar to be made, with observations for that purpose. Astrological divination was also an important part of astronomy. Astronomers took careful note of guest stars, which suddenly appeared among the fixed stars. The supernova that created the Crab Nebula observed in 1054, now known as the SN 1054, is an example of a guest star observed by Chinese astronomers, recorded also by the Arab astronomers, although it was not recorded by the European contemporaries. Ancient astronomical records of phenomena like supernovae and comets are sometimes used in modern astronomical studies. Cosmology. The Chinese developed three different cosmological models. The Gaitian, or hemispherical dome, model conceived the heavens as a hemisphere lying over a dome-shaped earth. The second cosmological model, associated with the Huntian school, saw the heavens as a celestial sphere not unlike the spherical models developed in the Greek and Hellenistic traditions. The third cosmology, associated with the Shanyi school, viewed the heavens as infinite in extent and the celestial bodies as floating about at rare intervals, and the speed of the luminaries depends on their individual natures, which shows they are not attached to anything. Constellations. The divisions of the sky began with the Northern Dipper and the 28 mansions. In 1977, a lacquer box was excavated from the tomb of Yi, the Marquis of Zheng, in Suizhan, Hubei province. Names of the 28 lunar mansions were found on the cover of the box, proving that the use of this classification system was made before 433 BC. As lunar mansions have such an ancient origin, The meanings of most of the names have become obscure. Even worse, the name of each lunar mansion consists of only one Chinese word, the meaning of which could vary at different times in history. The meanings of the names are still under discussion. Besides the 28 lunar mansions, most constellations are based on the works of Shi Shenfu and Ganda, who were astrologists during the period of warring states in China. In the late period of the Ming Dynasty, the agricultural scientist and mathematician Zhu Guangqi introduced 23 additional constellations near to the celestial South Pole, which are based on star catalogues from the West. Star catalogues and maps. Star catalogues. In the 4th century BC, the two Chinese astronomers responsible for the earliest information going into the star catalogues were Shi Shen and Ganda of the Warring States period. These books appear to have lasted until the 6th century, but were lost after that. A number of books share similar names, often quoted and named after them. These texts should not be confused with the original catalogues written by them. Notable works that helped preserve the contents include: Wu Jian has been one of the astronomers in debate. He is often represented as one of the three schools astronomical tradition, along with Gan and Shi. The Chinese classic text Star Manual of Master Wu Jian and its authorship is still in dispute, because it mentioned names of 12 countries that did not exist in the Shang Dynasty, the era of which it was supposed to have been written. Moreover, it was customary in the past for the Chinese to forge works of notable scholars, as this could lead to a possible explanation for the inconsistencies found. Wu Jian is generally mentioned as the astronomer who lived many years before Gan and Shi. The Han Dynasty astronomer and inventor Zhang Heng not only catalogued some 2,500 different stars, but also recognized more than 100 different constellations. Zhang Heng also published his work Lingjian, a summary of different astronomical theories in China at the time. In the subsequent period of the Three Kingdoms, Chen Zhuo combined the work of his predecessors, forming another star catalogue. This time, 283 constellations and 1464 stars were listed. The astronomer Guo Shoujin of the Yuan dynasty created a new catalogue, which was believed to contain thousands of stars. Unfortunately, many of the documents of that period were destroyed, including that of Shoujin. Imperial Astronomical Instruments was published in 1757 and contains 3,083 stars exactly. Star maps. The Chinese drew many maps of stars in the past centuries. It is debatable as to which counts as the oldest star maps, since pottery and old artifacts can also be considered star maps. One of the oldest existent star maps in printed form is from Su Song's Celestial Atlas of 1092 AD, which was included in the horological treatise on his clock tower. The most famous one is perhaps the Dunhuang map found in Dunhuang, Gansu, uncovered by the British archaeologist Mark Orlstein in 1907. The star map was brought to the British Museum in London. The map was drawn on paper and represents the complete sky, with more than 1,350 stars. Although ancient Babylonians and Greeks also observed the sky and catalogued stars, no such complete record of the stars may exist to survive. Hence, this is the oldest chart of the skies at present. According to recent studies, the map may date the manuscript to as early as the 7th century AD. Scholars believe the star map dating from 705 to 710 AD, which is the reign of Emperor Zhongzong of Tang. There are some texts describing the movement of the sun among the sky each month, which was not based on the observation at the time. Lunar and solar eclipses. Chinese astronomers recorded 1,600 observations of solar and lunar eclipses from 750 BC. The ancient Chinese astronomer Shi Shen was aware of the relation of the moon in a solar eclipse, as he provided instructions in his writing to predict them by using the relative positions of the moon and the sun. The radiating influence theory, where the moon's light was nothing but a reflection of the sun's, was supported by the mathematician and music theorist Jing Fang, yet opposed by the Chinese philosopher Wang Chong, who made clear in his writing that this theory was nothing new. Jing Fang wrote, "The moon and the planets are yin. They have shape but no light. This they receive only when the sun illuminates them." The former masters regarded the sun as round like a crossbow bullet, and they thought the moon had the nature of a mirror. Some of them recognized the moon as a ball too. Those parts of the moon which the sun illuminates look bright, those parts which it does not remain dark. The ancient Greeks had known this as well, since Parmenides and Aristotle supported the theory of the moon shining because of reflected light. The Chinese astronomer and inventor Zhang Heng wrote of both solar eclipse and lunar eclipse in the publication of Lingxian, 120 AD. The sun is like fire and the moon like water. The fire gives out light and the water reflects it. Thus the moon's brightness is produced from the radiance of the sun, and the moon's darkness is due to the sun being obstructed. The side which faces the sun is fully lit, and the side which is away from it is dark. The planets have the nature of water and reflect light. The light pouring forth from the sun does not always reach the moon owing to the obstruction of the earth itself. This is called an HSU, a lunar eclipse. When it happens with a planet inoculation, when the moon passes across, then there is a solar eclipse. The later Shang Dynasty scientist Shen Kuo used the models of lunar eclipse and solar eclipse in order to prove that the celestial bodies were round, not flat. This was an extension of the reasoning of Jing Fang and other theorists as early as the Han Dynasty. In his Dreamful Essays of 1088 AD, Shen related a conversation he had with the director of the Astronomical Observatory, who had asked Shen if the shapes of the sun and the moon were round like balls or flat like fans. Shen Kuo explained his reasoning for the former. If they were like balls, they would surely obstruct each other when they met. I replied that these celestial bodies were certainly like balls. How do we know this? By the waxing and waning of the moon. The moon itself gives forth no light, but is like a ball of silver. The light is the light of the sun. When the brightness is first seen, the sun alongside, so the side only is illuminated and looks like a crescent. When the sun gradually gets further away, the light shines slanting, and the moon is full round like a bullet. If half of a sphere is covered with powder and looked at from the side, the covered part will look like a crescent. If looked at from the front, it will appear round. Thus we know that the celestial bodies are spherical. When he asked Shen Kuo why eclipses occurred only on an occasional basis while in conjunction and opposition once a day, Shen Kuo wrote, "I answered that the ecliptic and the moon's path are like two rings, lying one over the other, but distant by a small amount. The sun would be eclipsed whenever the two bodies were in conjunction, and the moon would be eclipsed whenever they were exactly in position. But though they may occupy the same degree, the two paths are not near, and so naturally the bodies do not upon one another." Equipment and innovation. Armillary sphere. The earliest development of the armillary sphere in China goes back to the 1st century BCE, as they were equipped with a primitive single-ring armillary instrument. This would have allowed them to measure the north polar distance and measurement that gave the position in AHSIU. During the Western Han Dynasty, additional developments made by the astronomers Luo Ziyang, Zhang Yuangren, and Geng Shouchang advanced the use of the armillary in its early stage of evolution. In 52 BC, it was the astronomer Geng Shouchang who introduced the fixed equatorial ring to the armillary sphere. In the subsequent Eastern Han Dynasty period, the astronomers Fuyin and Jia Kui added the elliptical ring by 84 AD. With the famous statesman, astronomer, and inventor Zhang Heng, the sphere was totally completed in 125 AD, with horizon and meridian rings. It is of great importance to note that the world's first hydraulic armillary sphere was created by Zhang Heng, who operated it by use of an inflow clepsydra clock. A bridge armilla, designed by famous astronomer Guo Shoujing in 1276 AD, it solved most problems found in armillary spheres at the time. The primary structure of a bridged armilla contains two large rings that are perpendicular to each other, of which one is parallel with the equatorial plane and is accordingly called equatorial ring, and the other is a double ring that is perpendicular to the center of the equatorial ring, revolving around a metallic shaft, and is called right ascension double ring. The double ring holds within itself a sighting tube with crosshairs. When observing, astronomers would aim at the star with the sighting tube, whereupon the star's position could be deciphered by observing the dials of the equatorial ring and the right ascension double ring. A foreign missionary melted the instrument in 1715 AD. The surviving one was built in 1437 AD and was taken to what is now Germany. It was then stored in a French embassy in 1900, during the Eight-Nation Alliance. Under the pressure of international public discontent, Germany returned the instrument to China. In 1933, it was placed in Purple Mountain Observatory, which prevented it from being destroyed in the Japanese invasion. In the 1980s, it had become seriously eroded and rusted down and was nearly destroyed. In order to restore the device, the Nanjing government spent 11 months to repair it. Celestial globe before Qing dynasty. Besides star maps, the Chinese also made celestial globes, which show stars' positions like a star map and can present the sky at a specific time. Because of its Chinese name, it is often confused with the armillary sphere, which is just one word different in Chinese. According to records, the first celestial globe was made by Geng Shouchang between 70 BC and 50 BC. In the Ming dynasty, the celestial globe at the time was a huge globe showing the 28 mansions, celestial equator and ecliptic. None of them have survived. Celestial globe in the Qing dynasty. Celestial globes were named in the Qing dynasty. The one in Beijing Ancient Observatory was made by Belgian missionary Ferdinand Verbiest in 1673 AD. Unlike other Chinese celestial globes, it employs 360 degrees rather than the 365.24 degrees. It is also the first Chinese globe that shows constellations near to the celestial South Pole, the water-powered armillary sphere and celestial globe tower. The inventor of the hydraulic-powered armillary sphere was Zhang Heng of the Han Dynasty. Zhang was well known for his brilliant applications of mechanical gears, as this was one of his most impressive inventions. Started by Su Song and his colleagues in 1086 AD and finished in 1092 AD, his large astronomical clock tower featured an armillary sphere, a celestial globe and a mechanical chronograph. It was operated by an escapement mechanism and the earliest known chain drive. However, 35 years later, the invading Jurchen army dismantled the tower in 1127 AD upon taking the capital of Kaifeng. The armillary sphere part was brought to Beijing, yet the tower was never successfully reinstated, not even by Su Song's son. Fortunately, two versions of Su Song's treatise written on his clock tower have survived the ages, so that studying his astronomical clock tower is made possible through medieval texts. True north and planetary motion. The polymath Chinese scientist Shen Kuo was not only the first in history to describe the magnetic needle compass, but also made a more accurate measurement of the distance between the pole star and true north that could be used for navigation. Shen achieved this by making nightly astronomical observations along with his colleague Wei Pu, using Shen's improved design of a wider sighting tube that could be fixed to observe the pole star indefinitely. Along with the pole star, Shen Kuo and Wei Pu also established a project of nightly astronomical observation over a period of 5 successive years, an intensive work that even would rival the later work of Tycho Brahe in Europe. Shen Kuo and Wei Pu charted the exact coordinates of the planets on a star map for this project and created theories of planetary motion, including retrograde motion,